Hello! Today we have Pre-Calc Lesson 83, Simple Probability, Independent Events, and Replacement. So let's first do simple probability or simple prob. Probability is the study of outcomes that have equal chances of occurring. Okay, so we have these different terminologies. Experiment, right? Experiment is what we are doing. Flipping a coin, rolling a die, select a card, etc. Something like that. Okay, outcome is the individual response. Our sample space is the set of outcomes. And our event is the subset of our sample space. Okay, now it's a lot of terminology, okay, but we will be using all of those different terms in a little bit. Now, the actual probability of an event equals the number of outcomes that satisfy a requirement, like how many times can you flip a coin and get heads? Satisfying the requirement would mean that it is heads. Okay, and it's divided by the total number of outcomes in our sample space. Like how many times we flipped it. Okay, now probability of an event, we label it as P of E. Okay, there is parameters on P of E. The probability, the lowest probability that something can have is 0, right? It didn't happen, or it cannot happen. And the highest probability is 1. It happened every time. Okay, those are really our two options of our parameters, right? We can be anywhere in between. All right, so let's look at an example to make this more clear. Example 1, we have 2 fair dice, so they're not trick, are rolled. And what is the probability of getting, first let's look at getting a 7, and then second let's look at a number greater than 8. Okay. So for A, okay, we are looking at the probability of getting a 7. Okay, now we have this big chart that we can create, which is very helpful. Okay, this is my first dice. 1, 2, 3, 4, 5, 6. This is my second one. Right, we only have 6 possible numbers, okay, and if I roll a 1 and a 1, I get a 2, 3, 4, 5, 6, 7, right? 1 and 2, 3, 4, 5, 6, 7, 8, 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. These are all of the different possible outcomes. Now, we want to know, the first one, the probability of getting a 7. Now, we know that our total number of outcomes is 36, right? We have 6 times 6, we have 36 in this whole table. Those are our total possible outcomes. Now, the event of rolling a 7, we have 1, 2, 3, 4, 5, 6. We have 6 options of not rolling a 7, but when we add our dice together, they get a 7. which gives me that the probability is 1 over 6. Okay, let's look at the probability of getting a number that's greater than 8. Again, our sample space is 36. Okay, now greater than an 8 does not include 8, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 out of 36, which gives me 5 out of 18. Okay, that is the chart that we use for rolling 2 dice. Okay, it's really good to draw your chart because then we're never going to ever be confused about dice. Now let's talk about something different. Let's talk about independent events. Independent events are events that do not affect one another. If I do one thing, then the other is not based on that. One outcome is not based on the other. Okay? Now, the probability of independent events occurring in a designated order is the product of the probabilities of individual events. So let me write that out. This is the key. The probability of independent events occurring in a designated order is the product of the probabilities of the individual events. The product. And a key in this is our tree diagrams. It is the key to success. So let's do an example. A fair coin is tossed 3 times. What is the probability
please come to the front desk.
that it comes up heads every time? Okay, heads every time.
Sammy Parra, please come to the front desk. Sammy, to the front desk.
Sammy Parra needs to come to the front desk. All right, now in my first toss, I can either get heads or tails. It's a fair coin, so only heads or tails can happen. In my second toss, I again can get heads or tails for each of these. And my third toss, each of these can get heads or tails. Now, I want the probability of 3 heads, right? Heads every single time. Now, if I look at the end, 1, 2, 3, 4, 5, 6, 7, 8, I have 8 possible outcomes. Okay, at the very end, I know that I should have something like that. Now, the probability of 3 heads is the probability of 1 head times the probability of 1 times the probability of 1. So I know to get this first head, I have the probability of 1/2. Again, the second one, I have the probability of 1/2. And the third one, I have the probability of 1/2, giving me a total probability of 1/8. Okay. Let's do another example while we have this tree here. Okay, a fair coin is tossed 4 times, and it comes up heads each time. What is the probability it will come up heads the next toss? Alright, so already we have tossed it 4 times and it's come up heads each time. But my next toss is an independent event, meaning the first toss does not affect it. So when you flip a coin, you have 2 options, heads or tails. So the probability of heads is 1/2. Does not matter that I already had 4 heads. It's that one particular head. Okay? All right. Let's talk about replacement. Replacement is simply when an item is drawn, then it is put back. This changes our probabilities a lot. So let's do an example. An urn. I don't know why, but an urn seems to be a common container. You could say a vase, a pot, a bowl, a plate, a hole, I don't care. But your book likes to use urn. An urn contains 2 black marbles and 2 white marbles. So total of 4 marbles. A marble is drawn at random and replaced. Then a second is drawn. Okay, so the question, we have 2 questions. What is, let's call this A, what is the probability both are black? And B, if the first marble is not replaced, what is the probability both are black? All right, so think about if I am drawing out, okay, my first marble for A. Okay, the first marble I draw, I want it to be black, and I have an option of it being, this is the first marble, 1/2, right? Because there are 2 black marbles in there. Okay, so I can draw one of the 2. Now, the probability that the second is black is the same because I put the marble back in. So now the probability that both are black is 1/2 times 1/2, which is 1/4. Right? It's the same probability for both because I put my first marble back. So I have the same amount of marbles in my urn. Okay? Now for the second one, let's draw a tree diagram. So I have options. I have white and then black. Okay? This is my first draw. Then my second draw, if I choose the first marble as white, there's only 1 white marble left, but I have 2 black marbles left. And for my first draw, if I draw black, I have 1 black marble left and I have 2 white marbles left. Okay? Now the probability that they are both black, okay, if I look here, the probability that the first is black is 1/2. Now the probability that the second's black is 1/3, 1 out of the next 3. Leaving me with a total probability that both are black at 1/6. Okay? Does that make sense? Replacement versus not. Let's do one more example to have it make even more sense. Two cards are drawn from a 52 card deck without replacement. What is the probability that the first is red and the second is black? Okay, so probability red, then black. Now, if you know anything about a deck of cards, there's 52. Half of them are red, half of them are black. So my first option is to get a red card. I have half the cards to choose from. I have 52 cards to choose from. Half of them are red. Now, my sample space for the next one, okay, if I've drawn out a card and not replaced it, I only have 51 cards left. But my first card was red. That means I still have 26 black cards left. Okay, which if I multiply this out and simplify, gives me 13 over 51.